started counting the space between the atoms. And trillions of atoms later, they've nearly completed their task.
We hope that in 2 years we will have all the informations together for a new definition. That means we have a value with a very small uncertainty, let us say below 2 times 10 to minus 8.
And that's an accuracy to 8 decimal places. It's the same level of precision as Team Watt Balance in America are striving for.
At the moment we are in the, let's say, in the pole position to win this race.
Within a few years, Legrand K could be retired. But the work here could revolutionize another of the 7 fundamental units we use to describe our world.
Ein Kaffee mit Milch, bitte? Yeah, thank you. If the silicon team is successful, then they won't just redefine the kilo. They could end up redefining the SI unit most feared by chemistry students across the world, the mole.
It's a word which comes from Latin, meaning massive heap of material.
Now, chemists probably won't like this, but consider this cup of coffee. There's a certain ratio of milk to coffee, say 1 part milk to 9 parts coffee, which combined makes 1 part perfect milky coffee. Now, does a similar thing for chemists, but replace the coffee and the milk with atoms and molecules. Yeah, perfect.
All this leads back to our friend Dalton and his work in the 19th century. When he began his investigation into atoms, he discovered that atoms from different elements weighed different amounts. At the center of every atom is a nucleus containing protons and neutrons. Different elements have different numbers of these protons and neutrons, which is why they weigh different amounts. Throughout the 19th century, the greatest chemists of the day feverishly tried to work out the atomic weights of all the known elements. It led to one of science's greatest ever achievements, Dmitri Mendeleev's periodic table. And if you look at each element on that table, you'll see their atomic mass written just below them. It was a huge breakthrough. Chemists could finally mix and manipulate elements with newfound precision. But atoms are far too small to look at and manipulate individually. What chemists needed was a way of scaling up atomic weight into something more tangible they could weigh. And the answer was the mole.
The mole is really just a big number, a huge number in fact, which when you combine it with the atomic weight of each element, allows you to work out how many atoms there are inside something. It's the chemist's way of scaling up the microscopic world of the atom to our world of the gram. It's really the bedrock of modern chemistry, allowing us to mix things from drugs to fuel with such precision. But it leaves open one big question. Exactly how many atoms are there inside a mole?
The number of atoms that we have in a mole is what we call Avogadro's number. We can go back to Einstein, for instance, in 1905. He came up with one of the first estimates of just how big this number is, from looking down microscopes at pollen grains, and from that he was able to get one of our first estimates of the number. He got the first number right, he got the 6 right, and he got the 23 zeros right.
While Einstein's groundbreaking work got close to defining the elusive Avogadro's number, it's the silicon sphere team that could not only solve the kilo conundrum, but also solve the centuries-old question of how many atoms there are in a mole. once and for all, define Avogadro's number. If this happens, it will be a remarkable moment in measurement history. In one astonishing experiment, 2 golden units of measurement could be redefined.
We've come a long way since the days of using barleycorn weights. Our quest for ever greater precision has led us into the very fabric of our universe, allowing us to weigh and analyse things with incredible speed, scale and precision. In a few years' time, all going well, the BIPM will decide between atoms or electrical force to redefine the kilo. It's kind of irrelevant. Both Team Watt Balance and Silicon Ball have done what seemed impossible, to redefine the kilo based on the unchanging laws of the universe.
In the pursuit of ever greater accuracy, these remarkable projects have brought together thousands of years of scientific endeavour. But our quest for ever greater precision doesn't stop here. The last great measurement frontier will be to journey inside atoms themselves, to discover what mass really is. "100 meters under the Swiss-French border, at CERN's particle accelerator, scientists think that they've discovered a particle that gives things mass, the Higgs boson. And one day, our human desire for ever greater precision may even see mass redefined once more, and tied to Higgs itself.
If it happens, who knows what the technological impacts will be? And that's the beauty of measurement. Every leap in precision leads to new scientific and technological advances. Measurement has shaped our history and will continue to change our world.
Next, we explore the world of energy and how the measurement of light, heat and electricity have transformed our lives. As I continue my journey into measurement.